Great, thank you. So actually Dave Hannay was asked to talk about the underwater listening station and Boundary Pass, and he couldn't be here today, so he asked me to give this presentation. So thank you for the opportunity to do so. Again, I'm Melanie from JASCO, and Harold already introduced me. So the Boundary Pass underwater listening station, this is a multi-year project that's sponsored by Transport Canada, and with strong collaboration from the Port of Vancouver ECHO program. So the underwater listening station is located in the shipping lanes of Boundary Pass, and it's a cabled system that runs to shore on East Point at Saturna Island. And the primary goals for this project are first to conduct accurate calibrated measurements of noise emissions from thousands of large commercial ships transiting through Boundary Pass. Then also to detect and localize calling marine mammals, and to measure ocean noise levels and look for changes in those levels over time. So seasonally throughout the year, as well as changes from year to year. So these data have been collected since 2018, starting in December. And initially we had autonomous recorders deployed while the cabled systems were being developed and built. And the cabled systems were deployed in May of 2020. And then we've had continuous real-time data 100% of the time since May 2020 through now and ongoing. So why Boundary Pass? So there was a feasibility study in 2017 that was led by Ocean Networks Canada, looking at different candidate locations and assessing different site conditions. And this location was chosen. Some of the key reasons, one being the water depth is deep enough. The hydrophones are in about 200 meters of water, which allows us to do the ship noise measurements using protocols that follow international standard. As well, the shipping lanes are adjacent in this location, so we get measurements of inbound and outbound ships using the same recorders. And importantly for this workshop, Boundary Pass has a relatively high occurrence of southern resident killer whales. So that provides an opportunity for studying things like whale behavior and vocalization in the presence of ships. So the shore site again is on Saturna Island. The hydrophone arrays are about 2.5 kilometers offshore. So we have cables running to shore from those locations to a base station on land, where all the data is received in real time. There's some processing done on shore, and it's all stored in a database. And then the data are also available through a web interface. So at any time, people with access to the website can log in and see the data coming in real time. In addition to the acoustic data, there's also various oceanographic data that are collected as well. This is a video just showing that's one of the hydrophone arrays when it was being deployed. So we had a cable lay vessel come in and lay the cables and then set the arrays in place. Again, this was in May 2020. And this figure is just sort of showing a schematic of how the system is set up. So there's the two arrays, they're like tripod frames. They each have 4 hydrophones, and they're separated by about 300 meters. And again, the intention is to measure the sounds being emitted by the ships as they travel overhead, and then as well, any marine mammals that are vocalizing in the vicinity of the arrays. So for acoustic data, as I mentioned, each tripod frame has 4 hydrophones, so 8 in total. They're all sampling at 512 kilosamples per second. So we can characterize acoustic data up to 256 kilohertz. And it's all 24-bit data. So this is a tremendous amount of data. We record about 1 terabyte of data each day. In addition to the acoustic data, we collect ADCP measurements for currents, CTD data for temperature and salinity, which determined the sound speed, as we heard about this morning. Each frame also has a video camera, and on shore there's an AIS receiver to receive AIS data from the ships, so we can identify what ship is passing and how fast they're traveling, all that sort of information. And we collect weather data from East Point Park Weather Station, which is about 3 kilometers away. So as I mentioned, this is all fed into a web interface. This is our Port Listen software, and it has sort of 3 data streams or 3 apps that can be reviewed. So there's ambient view for reviewing the ocean noise data, looking at just all the general underwater noise and trends over time. The PAM View app is used to review marine mammal detections, and the Ship Sound app is used to review all the measurements of the vessel noise emissions. And again, that's updated in real time. So at any time you can log in and see all the past data up to the data collected within the last 5 minutes. This is showing a screen of the Ship Sound interface. So using the AIS data, we track each passage of each large AIS emitting vessel and generate and calculate source level estimates for each ship. And we calculate both monopole source levels and radiated noise levels for people that know the difference. And we calculate those in 1/3 octave bands. And for each vessel, over to the right is shown like a report card sort of, or a noise report for each vessel. So we give the source levels, there's the details about the ship that again comes from the AIS data. So it's class, its size, information like that. And then information details about the measurement. So the date and time, the speed the vessel was traveling, other relevant information about the measurement. So we have over 20,000 vessel passes have been analyzed using this software. We measure approximately 17 new measurements each day. And the measurement protocol and the analysis protocol is consistent with measurements that were done between 2015 and 2018 for the ECHO program in the Strait of Georgia, which had around 7,000 additional measurements. So together, this comprises the largest database of this high quality of measurements of ship noise probably in the world, and it continues to grow every day. So this is looking at the interface for looking at marine mammal detection. So this is what we're here to talk about today. So first you get a plot showing a timeline of detections. So the system runs 4 call detectors that are based on a random forest approach. And those are running in real time with detectors for humpback whales, killer whales, Pacific white-sided dolphin, and fish-like sounds. And so you can click on any of the peaks in the time history where you want to focus in on specific detections. You can select a specific time range and a species of interest. And when you click on that, you then get this more detailed view that brings up the spectrogram. You can listen to an audio clip. An example of a killer whale call. And so we have analysts that go in regularly and review all of these detections, verify that it was identified correctly. They can adjust the species if necessary. And then there's a verification status flag. So you could filter to just look at accepted or validated detections, or you can review all detections. And it describes what detector was used. Yeah, the system also has the capability to do localization, but that is not yet implemented in an automated fashion or in real time, but I'll talk about that in a moment. I'll talk about that right now. So we have been starting to look at doing localization of the calls. So these are examples of localizations of echolocation clicks. This is using a time difference of arrival approach. And so the clicks are nice to work with in this way. Looking at the lower frequency calls and whistles gets a little more tricky because they overlap in time. So for this initial investigation, we've been looking at clicks. So the top panel that has the red and blue dots, those are showing click detections on the two different arrays. So blue is from one array and red is from the other. And you can start to see individual tracks that join up. So you can start to track individual animals using this method. So here we're looking in the horizontal plane. So we have direction or distance in the X direction and on the horizontal and in the Y direction on the vertical. In the bottom, that's the same data, it's just split out now. So data from array A, or the red dots, are now in the left panel, and from array B are in the right panel. And now the different colors are showing different time. So blue dots are earlier in time and red dots are later in time. So then that allows you to see the direction that the whales are traveling as well. So quite a lot of really valuable information can come out of these data. And there's a lot more to be learned from this, but this is the type of thing that would feed nicely into the forecasting model. So now instead of just having a single hydrophone where you get a detection and the whale could be anywhere within, say, 4 kilometers around that hydrophone, taking it this next step to localizing where the whale is and which direction it's traveling, I see being sort of the useful information that would feed into the forecasting model. So this allows, again, tracking individual animals from pods and groups. You can look at group distribution, swim speed, dive depths, direction of travel. I'm sure there's other movement parameters that can be teased out of this. And then also, since you get a location, and so therefore a distance from the hydrophone, we can also estimate source levels through this analysis. And as Harold mentioned, I think southern resident killer whales are highly vocal, so they're a good species for doing this type of analysis because they have high vocalization and echolocation rates. So I also mentioned each frame has a video camera mounted on it, and we collect 3 minutes of video data each hour. So we have lots of footage of different fish and benthic animals that pass by the arrays. This is just some fun video of a giant Pacific octopus that was recorded in June of 2020. So it's pretty neat to watch that. So this allows correlating sounds that we record with presence and location of animals at the times that we hear the sounds. To date, we haven't really done very much in-depth analysis of these video data, but we're hoping moving forward that some students can get engaged to start diving into this video data as well. So just to wrap up, I wanted to just describe some of the ways that these data are being used and have been used and can be used in the future, to sort of highlighting the value of this type of data collection and applications for these real-time data. So first, the ECHO program with the Port of Vancouver, they review all of the ship measurements and identify unusually loud vessels, and they can use these data for making management decisions and sort of informing their programs. Some other studies, again, through the Port of Vancouver, there's been a vessel noise correlation study. So looking at that extensive database of vessel measurements and looking at how the sound emissions vary by vessel type, vessel size, transit speed, also variation of the same vessels. We have multiple measurements of the same vessels, so looking how those change between measurements and what factors might be affecting that. You've probably heard about a voluntary vessel slowdown study, again, through the ECHO program. So as vessels travel through Boundary Pass at certain times of year, they're asked to voluntarily slow down. So we've been looking at how the sound is reduced by reducing the vessel speeds and looking at the environmental benefits of doing that. This, I think, leads into the question from the last talk. So there has been some work done at doing localization of vessels. So from these vessel measurements, using similar approaches to localizing whales, you can localize the vessel noise as well. And this study was looking to see where, specifically which part of the ship is emitting the noise. So the top plot there is showing on the horizontal, that's distance forward of the stern. And then on the vertical is distance, I guess, across the ship, you could say. So this is just highlighting that the sound really is being emitted at the back of the vessel. So it maybe seems intuitive, but just confirming that the vessel is coming from the engine and the cavitation at the propeller right at the stern of the vessel. Harold had mentioned the playback studies that he was doing. So there were recordings on the ULS of his killer whale playback data. So he's been using the ULS data in their work. And then we've been working on killer whale classifiers and feeding this information into the work being done by Ruth and probably others in the room, looking to feed this into the machine learning algorithms as well. There's ambient noise studies. So each panel here is 1 month of ambient noise data, and these are power spectral density curves. So looking at the sound levels in different frequency bins from January in the top right down through to December in the bottom left. And I think this is 2020. But so again, you can look at changes of the sound level from month to month throughout the year, and then you can compare that from year across year as well. And then lastly, there's a quiet ship notation work that's being done, again, with the database of vessel measurements, where we're consulting with different ship certification societies to help them in establishing protocols for measuring ship sound levels for consistency across the different societies, and also looking to establish thresholds or targets that for building of new ships, that they should be targeting specific noise emission thresholds. And so this is the kind of information that can be used, have an impact globally, not just in the local region. So I think I'll just finish with acknowledging all the people that assisted with the installation and the operation of the underwater listening station, and then of course notably Transport Canada and the Vancouver Fraser Port Authority for funding the work.